I started in Spanish, but I don't know how to speak Spanish, so after a moment it could be difficult for me. So, as I told you, this is an important problem that can be generalized to other topics. So what I will talk about has several applications, really several applications, very interesting applications, and deals with fundamental problems. Usually, when we work on images, when we perform image processing, we use gray level images. We say also scalar images. That is an array in which we have single values that can be integer, that can be floating point, and so on. So that's usually what we do when we talk about Sobel operator, when we talk about Laplacian and so on. Usually we work on grayscale, gray level images. In this case, I will talk about color. So, color is a 3D representation of the reality. Why is it like that? You know, I think you know that it's mainly because our eye catches information, catches data, and extracts information from 3 channels related to the cones we have, that are the cells that filter the signal. That's okay? Do not hesitate if there is any problem to ask me. Okay? So, color is mainly a 3-dimensional signal, 3-dimensional data. But we know also that most of the information is carried in the grayscale information. When you watch the TV, for example, and if you see a soccer game, and if you see on the black and white TV, you understand what happens. And even you see the goals and everything. But you understand everything. So color brings some additional information. Okay? So, in some applications, there is a fundamental problem that is how to catch coherent color and coherent areas. For example, here I am on this stage, and it is brown, here it's more or less gray, and so on. By this way, if we have a camera that takes, or video camera that takes a picture of, or a video sequence of this area, of this 3D scene, there will be some blue, some brown, and so on. And if we want to catch automatically the speaker, we will not focus on the blue areas, but on the brown area. When we watch a soccer game, hello, hola. When we watch a soccer game, we can say the following thing, using a video camera or using our eyes, for example. We watch at the game on the field, and the field is of a given color. It may be green when there is grass, or it may be also brown if there is earth, and so on. And this color, we can find it also in the stages, in the other areas. But what we can say is that where the soccer players play, it is an area that is globally of given color and globally coherent. Suppose if you have a video camera on a square and there is a given area on which you want to focus, you will select this area, and you can select it because it is coherent about this color and about its area. So this is a problem that has a lot of applications. And it's not a very easy problem. It's not something very easy to do, because, for example, if you watch a video sequence of a soccer game, there will be some areas that will be in the dark, and some areas with a very light green. And the very light green may be closer to the blue than to the dark green. So how to select these colors that looks similar, although that in the color space they are not the closest one. That is the purpose of the talk I will give you. Also, when you watch a game, you can have trees around the field and you don't want to catch the green of the trees. And you have soccer players who are not green, except if they come from Mars. But usually it's not the case. And so they have a suit and so on. So how to collect, to extract this information, that is, there is a main area with a main color that you understand as a main color. Okay? So, that's the title of my presentation, Characterization of Coherent Colors color areas in an image, and application to soccer field detection for a simulator. You remember 2 days ago, for those who were here, that I talked about a simulator for soccer we have designed, and we used this, this process, this algorithm, to detect the field on the soccer, on the video camera. So here is a problem. I don't know if you can see very well. So the problem is the following one. We have a 2D image, and this 2D image, that is an image of the video sequence, is, as you can see like that, these players, but you can see also there is the audience, and there are some advertisement, and so on. And we have a 2D model on the right, on which you want to make the simulation. That is, you have the model. Yes, thank you. Muchas gracias. So, on the right, thank you again. Thank you more and more. So, on the right, what you have a model that has been visualized, but what is important to notice, it is that it is a model that you can manipulate, you can visualize in different ways, and on which you can put players that you can represent in a given way or more realistically and so on. So, what we want to do is to extract the players from these images, but from the left image. But once you have extracted the player, there is to put the model of the player on the model of the field, and that is a difficulty. So one of the problems is how to, there are several problems. One is how to detect that a person is a player. For example, there are persons in the audience and there are not players. So the reason that a player is a player, the person is a player, is it because it is on the field? And so first of all, we have to detect the field, and the field looks at something of a given color that is coherent on a coherent space. That is the first point. Then, once we find the location of the players, we need to make the image match with the model. There is a property, I will not give details on that, that a video camera gives a projective projection, what we call a projective transformation of a 3D model. And this is done through a 4x4 matrix, that is by a linear application, in what we call the homogeneous space. I don't know if you know about that. That is, you have a projective space. A projective space is a space in which there are points at the infinite, there are parallel lines, crosses, and so on. So the projective space has a representation through an homogeneous space. And there is what we call projective geometry. And there is a property, there are several properties that are very, very important. So those who use, for example, OpenGL know that there are matrices even for translations and even for perspective. That's because we handle that in the homogeneous space. That is, for 3D, a 4 by 4 matrix, because any projective transformation in 3D is represented by a linear transformation in the 4-dimension homogeneous space. And there is another theorem that says that when you have a 2D image in the 3D space and a 2D model in the 3D space too, and when there is a projective transformation from one to the other one, that from the image to the model, for example, from the model to the image, if both of them are 2D, so the transformation is represented by a 3 by 3 matrix. So I tell you that because what we need to do is to find a way to make the matching between the image and the model. And we know by this theorem, that there exists a transformation, a linear transformation in the homogeneous space that sets a correspondence between these two spaces, that are the image and the model, through a 3 by 3 matrix. And we need to find some landmarks in order to solve the system and to make them match. Okay? So, just to set the problem of the soccer simulator. We have a 2D image. We have a 2D model. In the model, we know some things, as for example, some landmarks. For example, some points as the corner point or the goal line and so on. So we have some landmarks we know. We have to detect some landmarks in the image. And then when we have enough pairs of landmarks, we can make the transformation. And once we have detected the players on the image, by using this transformation, we can put them in the model. So, just to summarize the problem, we have an image, we have a model. On the model, we have some knowledge, which are, for example, the location of the lines and so on. On the image, we know what we want to look for. We want to look for some landmarks and also the players, but first of all, the landmarks. And when we want to look for them, we have to look for them only on the field, because there are other persons in the audience and so on, other lines outside and so on. So we want to reject these other elements. So the first question is how to find the field. Okay? So, in this case, it gives something like that. We find, in the same way, the player location. And then, once we have a model, we can go around it, for example, and watching them from another position and so on. So all of that requires a lot of skills in different areas as image analysis, pattern recognition, geometrical modeling, visualization, and even ergonomics, because as I told you 2 days ago, we don't want to do something as FIFA 2000, I don't know, because I lost the time since I started to play with FIFA, soccer FIFA. So we don't want to have very nice pictures of players. We want to have visualization that communicates an information, a relevant information to the end user. And what we did was for coaches. So in some cases, as I showed you like last time, it's better to have some objects to show the player location that gives a good idea of the strategy and so on. So we could not have that with very nice pictures. So that's what we want to get. As I told you, we start, I took another image, for example, in this case, and we want to detect lines. We know that in the model we will have some lines, and we want to detect these lines. We have no time in this charla, in this conference, in this talk, to see how we do that. but if you are interested in that, maybe another time you can do it. So we use the F transform. I think that some of you know about the F transform. F, it's H-O-U-G-H. And this enables to, it's written on the right. So we can use different, various way to process that. And that's not the purpose of the talk. So for example, we can use a Laplacian filter, but we could use a Sobel filter or anything like that. And then we can use F transform, and then we get a set of lines. And you can see on the picture on the right that there are a lot of lines. And all these lines are relevant. But for example, you can see that there is a wall all around the field, and the line that is the upper bound of the wall is really a very significant, a very relevant line that has been detected by image processing. But this line is not a line drawn on the field, for example. So we want to reject it. And how to reject it? It's because it doesn't belong to the field. So, on the right picture, you can see a lot of lines, some of them on the field, some of them out of the field. And our purpose is just to select those that are in the field. So, as you can see, now, you see the previous picture like that, and now we are interested in finding this area, and we can succeed to do it, and I will show you how to do that. So, there are two criteria we use. We use the color coherence and the area coherence. Color coherence, as I told you, is that we look for something that is of the same color, but of the same color is something very difficult to say, as I told you. In this case, it's green, but as I told you, for example, a green area with a lot of light looks like white. A green area in the dark, in the shade, is almost black, and other colors can look similar to that. So I will show you how to make this selection. Once we have found the color coherence, you can see that there is the shadow of the players. The players are not green, and it's normal. We do not consider them as green. But once we did that, we use a special coherence, and we find on the right the field by this way, and so we can validate this area. So now I will leave a little the soccer to take other picture, because I don't want to focus only on that, because it could seem that the research works have been done only for soccer. And these research works are made for any kind of color, any kind of situation. So let's go through other pictures. On the picture on the left, it is about tennis, and we can say that what happened on the tennis court. So we can say there is mainly a big area that is orange, and something else that is green, but we don't care. The clothes, and the clothes is partly blue, oranges are orange, and on the right there is a white area with some drawings on it. But it's mainly white, even if there is blue also. And we want to put in evidence this information. On the right one, it seems a bit more complex, because we have globally a flower that is red, and around that there is one main color that is green, but there is a texture with other colors inside. So, we will show that we can select the color in areas like that in color coherent areas, and we can then discuss on that, or we can have in the program, in the process, depending on what we look for, we can have something to tell, okay, that's a soccer field, okay, that's an orange on, or oranges on clothes and so on. So let's take a fourth image like that. So this image is, I think it is a golf area. I think so, I'm not sure, possibly. So there is some sand or some earth, I don't know, that is almost white. And there is the sky that is blue, and there are different kind of green. And you can see about the green that you have dark green and light green. So, I just some water. So, we can have a first idea. This idea should be a good idea, but it's not a good idea. And we can see that on the right, it doesn't work very well. So the first idea should be to do like using an histogram of these values in a color space. Here we have taken the HLS, that is a hue, lightness, saturation space, but we could take any other space. We took HLS space because it's more relevant to understand, to visualize the color. But the result should be quite similar if using RGB space or CMY space. And so we just count the items, the occurrence of the pixels in this space. So when I find a value of a pixel that is red, green, blue, we transform it in HLS, and we put a value in the HLS space. Then we simply count all these values, and we make a threshold, and we give the value 0 to all the pixels that do not belong to the selected area in the HLS space. This gives not very bad result, but it gives this result on the right, with a lot of pixels that should be blue and that are not mentioned as blue, and so on. So, it's not so good like that. The reason is the following one. When you have, suppose you have a given value of blue, for example, that is with, if we consider the values of blue between, of red, green, and blue on one byte that is between, for example, 0 and 255. We can say we have 255 for the blue and the light blue, so maybe 150 for the red and 150 for the green. Okay? If all the values are like that, you will have a big amount of this triplet, okay? But if you have the same thing with values that are a bit different, for example, instead of having 150, you have 149, 151, and so on, you will get a set of values all around this value, and these values will not be detected because there will be spread around the initial value. So finally, when doing that, we see that we have a problem of high frequency. And one solution should be to smooth the histogram by using a low-pass filter. Is it okay? Okay. If you have any question, do not hesitate to ask me. So how can we perform, or how can we provide a low-pass filter? Simply by using a digital representation of the HLS space. That is, instead of looking for the exact value of RGB or HLS, for example, we want to catch all the values that are similar, that are close in a single cell, like we do in the F transform. You know, I think you know about the F transform. I talked to you about that, so I don't know. But in the F transform, you have cells, and you vote for a cell, in some way you vote for a cell, and we do the same thing here, and it provides a kind of low-pass filter. So let's see a new vision of the HLS space. The HLS space is supposed to be continuous. In fact, it's not continuous because there are single values. Even if there are 16 million values, it's not continuous. But let's say it's like continuous. In our case, what we do is that we consider cells in which we vote for the cell. So when we have RGB values that are, as I told you before, if they all have the same values, it will give a given amount in the cell. If the values are close one to the other, then we give the same value in the cell. So, as I told you, considering the HLS space as a digital space, we perform a low-pass filter on the histogram we had before in this space. And in this case, it will give some better results. So, what we consider here, you see, for each cell, so the set of cells is a partition of the HLS space. For each cell, we consider the center of the cell, and all these points that are the representatives of the cells, there are votes on them. The vote is we add 1 at each time that the HLS value for a given pixel is in this cell. So if we have an image of 1000 by 1000, we will have 1 million votes, and all these cells will have a value that will be a discrete set of values for representing all the colors of the image. So in this case, we get much better results. On the left, you have the initial image. In the middle, you have a representation of the discretized and thresholded HLS digitized space. That is, when we have a set of cells that provide a partition of the HLS space. We have a set of centers of the cells, or representatives of the cells, and in this case, in terms of visualization, we discussed about scientific visualization yesterday. So, in terms of visualization, here, I've represented with these spheres all the selected cells. And I represented them by their representant, that is a point with a given radius, and the radius is related to the amount of pixels that belongs to these cells in terms of HLS values. Okay? So, we do the following thing. We count, we vote for each cell, and then we make a threshold on that, and we can see that there is a big blue value, that is the sky. There are a set of sphere on the upper part that are the sand of the earth, and green values that are the grass. This picture is much better than the previous one. I can show you the previous one again. So watch this one, and that was the previous one. So you can see there are more black points on this one than on this one. But anyway, it's not correct because there are still a set of points that are supposed to be white that have not been considered as white here, and that is not good. So at this point, we have added two following ideas. One main idea and another idea, and we get very good results. So, I don't know if you know about Parzen windows, or Parzen Rosenblatt windows. Can you tell me like that, those who know about that? Okay, so I give you just an idea of that. In signal processing, the Parsen window, or Parsen-Rosenblatt window, will give you the opportunity to mix signal by propagating a discrete value in a continuous way. That is, instead of considering each pixel of the image that gives a given value HLS in the HLS space, even if instead of going on a given position, we vote in a given area. So instead of doing that, we consider that each of these pixels is not a punctual value in the HLS space, but a potential generator in this space. Instead of taking a value and I say, okay, I add 1 in this cell, or I add 1 in this location in the HLS space. Instead of doing that, we say, at this location in the HLS space, we consider that this point generates a potential. This potential can be very simple. It can be a decreasing value, that is a linear value, that reaches the 0 value after a few locations, you see very close, but it gives a potential. And this potential, so each point contributes to the potential. And finally, adding all this potential gives a function that is a continuous function, a potential function that is continuous in the whole HLS space. And a pixel that is a bit close to an area contributes also smoothly to this other area. So this can be visualized like that. You see, this is a section of the HLS space. In this case, you remember HLS is three-dimensional space. So the lightness is like the Z value or Z value, like that. And if we consider a given section that is for a given lightness, you have the U that is red, green, blue, yellow, and so on, by rotating like that. And the saturation, S, that is 0 when you are in the center of the section, and that is 1 when you are in the outer part. 0 for saturation means that we are in grayscale. 1 for the saturation means that we have a very, I would say like a flash, you see the green, very green and so on, red, very red and so on. So this is a visualization of a display of the discrete representation of HLS in a given section at a given level. We can see the centers, the one in red, for example, here. Here, this is the center of a cell, for example, like that. And this is a representant, so these are the representatives of these cells that compose the discrete representation of HLS. And here you have 3 pixels, P1, P2, and P3, that are 3 pixels of the image. And instead of keeping their value or adding 1 at their position, or instead of contributing by a vote to the cell, instead of that, we consider them as a potential, and we see that on the right. So for example, in this cell here, you see, we can see, no, it's not exactly the same, okay, in this cell, we have the contribution of 3 points, a very strong contribution of this pixel, medium contribution of this pixel and a very low contribution of this pixel. But by this way, there is a kind of communication, and this is exactly what is the spirit of Parsons-Rosenblatt windows in signal processing. So, when we use that, we get a continuous function in the HLS space, and now we come back to a digitized representation because we just consider the potential value as the representative of the cell. And this gives a set of values, so it's exactly the same image than before. You remember about the blue that there were only one sphere, and all the other positions on the side were lacking, where we missed this other position. By this way, we propagate a little bit information of color to the neighbors, and we can grasp the neighbors. And so, you can see that on the left, you still have the same image. In the middle, you have the representation after thresholding the potential on the HLS space after using this Parsons way. You see Parsons? It's written on the next slide. And then we have a much better result on the right. So, one question is, how do we do the threshold? Because I have repeated sometimes, we do a threshold in the HLS space, so we use something quite classical that uses what we call a segmentation of the cumulated histogram of values. This is what we see. Sorry, there is something written in French. So, on the left image, if we sort these values by decreasing values, you remember, for example, here, I come back in the previous image, or in this image, you have the big blue value, you consider the first one, then a green value or white value, and so on. So if we do like that, we have an histogram of values, and this histogram of values consider, first of all, the important contribution, and so on. And then, if we do the cumulated histogram is like the integral. You know the integral, like integral calculus. Okay? So, in this case, you have a growing function, but this growing function has a breakpoint that is like that, because at the very beginning you have the main error. Sorry. Oh yes, it's because I'm not in front of it. Yes. So this is a breakpoint. Here you have all the important contributions, and then you have the low contribution. And we know how to find this breakpoint because we, for example, what we can do is a split and merge algorithm. We can use a split and merge algorithm. For example, we can draw a line between this point and this point. This is a representation, a single line, and then you look for the farthest point and so on. And then after a set of division like that and merging, you get this point. So by this way, you do the threshold. And I told you also, and this is very important, I told you also that we have to find about the color coherence. And if you can see it, maybe some white values are close to the blue. Look. For example, this blue value is maybe closer to this white value than to this other blue value. This green value is closer to the blue value here than to the dark value that is here. You can see that. Okay? If we just use the distance between the colors, we can separate really the green that can be dark or light from the blue and so on. But what we do is that we look for shapes inside the color space. And the first way to look for shapes, there are other ways to do that, is to use connectivity. So, in this case, this point is connected to this one, that is connected to this one, that is connected to this one, that is connected to this one, and to this one. But there is no connection between the blue and the green here. So, by using connectivity, by using the connected component, we can find, and these are the relation of connectivity, because you remember that it is not something obvious as, for example, splitting a square or a cube in regular parts. In this case, there is something a bit complex in the digital representation of the HLS space. So, by using this rule of connectivity, like that, we can connect all those points that could go, for example, from the white to the black. Suppose there are a lot of green from the black to the very white, I would say, green. We could connect them and separate them from red and so on. And the result here is the following one. By using this, we have the initial image, and there are areas that are considered without color coherence. And you can see that these dark points, we don't know to which color they belong, but it's much, much better than what we had at the very beginning. You remember? So now we can use what we call the area coherence, and for that, there are very classical way to do it by using what we call mathematical morphology, for example, as dilation, erosion, that gives opening and closing and so on. So we have found 3 areas. There could be some green in one part, on the other part, for example, but there are 3 colors and also 3 areas, but there could be more than 3 areas. And by using this mathematical morphology operation, transformations, we get the image that is on the right. So this is very interesting because at the very beginning we had a very poor information extraction. Now we have a very good information extraction. And what is interesting also is that we do not use knowledge for that. We don't know that there is grass, or that there is sand, or that there is something else. This is very important because we could extract the information. So you know the difference between data, information, knowledge, and intelligence. Information in some way, it's what we can extract from data without knowing to what it is related. And knowledge is a representation of the world. Let's say here we know it's about golf, or before about soccer and so on. And so we bring that, we carry that into the model. And the idea is to make the matching between information and the model that represents the knowledge. So in this case, we don't take care of the fact that the terrain is green, is blue, is yellow, and so on. There is a sky, and so on. We just found the main components in the image that are with coherent color and coherent area criteria. So let's go back to the first. So you remember what we had at the very beginning, like that. Okay, on the right. And what we have now. That's better. From that, for example, if you have images of golf, you can say, yes, this is the bunker area, this is the sky, and so on. And then you can find there are birds in the sky or ball in the bunker, and so on. Let's go back on these images like that. So by this way, we find the tennis area, And you see that there are maybe, let's say, several persons, at least 2 players, but also some persons in the background. And in this case, you can see that we can extract the field and find where is the player and automatically find the player. So you can see also that here, on the second image, we consider that the main color in the, that is coherent on the right is a white, or something like white, that is not exactly white, but this is much more important than the green stuff we had inside, and that is what we perceived as human beings. So now, if we go back to our soccer field, you remember that we have extracted the field by this way, and it works very, very well. It's a very robust process, very robust algorithm. Once we have done that, we can find the lines that are on the field. Having these lines, that the lines that are extracted in some way, they represent information extracted from the area of the field. We can make this information match with the knowledge model, the knowledge representation. That is, we have a model on the right, for example, and we know, for example, in the model, these points are known. You see, all these points are known, their location, the distance, and so on. These are landmarks. These are landmarks we detect automatically because we detected lines and we validated them in the field, and we do not take, for example, this line or this line here or this line here. Once we have a set of landmarks automatically like that, we use also some properties of the projective space to find their organization. There is what we call the cross ratio. I will not talk about that, but we have a way to find the organization, the way they are organized, they are related, and so we can find the 3 by 3 matrix. You remember I talked to you about that. That is, from this to this, if we consider the 3D space, we have a 4 by 4 matrix, but in this case, we have an image on the left, we have a model on the right. All of them, both of them are 2D, and so we know that in the homogeneous space, a 3 by 3 matrix will set the correspondence. And once we have done that, automatically, we have exactly the representation of the scene. For example, you can see this image, as you can see, we choose different colors for the green. So you can see here there is some dark green, some light green, and so on. So we, on purpose, we choose different green here. So the left part of the image is a true image, a genuine image with a goalkeeper and so on. And the right part is a processed image, that is, we have replaced, we have found the correspondence and so on. And then we have put other players on there, and you can see that the lines correspond perfectly and so on. That's normal. And we put some other advertisement. This is the sign of our laboratory, for example. And we make it for tablet. Up to now, it's not a product because it's very complicated to make a product. Let's say we have a prototype that works very, very well, and even famous coaches used it and liked it a lot, but we had not a commercial structure. We had not the engineers to develop and to maintain the product. So right now, it may be done. We don't know, but it's in process, but it's very difficult. So maybe someday it will be used by the very famous coaches for soccer. And now the last one is, muchas gracias por su atención. I think I'm in time 50 minutes, 55 minutes. So if you have questions. Meanwhile, I would bring a little bit. Yes.
Since we are dealing with 2D image, that's good for the players, but what happens with the ball?
Oh, that's a very good question. It's supposed to be players that do not play with the ball. No, I'm just kidding. So, in fact, we have not a 2D model, but a 2D.5 model, because even the players can jump, can do things like that. And the ball is a problem, but we can use more sophisticated ways. In this case, we have not a 3x3 matrix, but we have a compound process in which we have this, and we try to guess what is the trajectory of the ball. So this is really a problem. But in fact, the ball is important, but usually the location can be inferred by knowledge. For example, if a player does like that, we know that the ball stays on the ground. If the player does like that, the ball can go there, so we can try to find where it went, but also we can find when it goes down and try to find the trajectory. As a matter of fact, on this project we worked with someone, with a specialist of soccer and sports, with a professor at the university in this field, and the scientific field is ergonomics. And what he was interested in for this project, and also the coaches, was not the location of the ball, even if it is something important, but it was why soccer players do not do the right thing. For example, why they are out, how do you say in English, out of hors-jeu, out of the line. You see, they run before, after the line, foul, yes. So they wanted to know why a player could go in between other players and catch the ball. So who did the bad thing? And for example, one thing they did with that, and so I told you that this has not been used in a commercial way because it was very difficult to go to commercial structure and so on, but it has been used for research in the field of soccer at the University of Marseille. And for example, they were interested in the skin between the location of players. So you remember we found some players like that, and they wanted to know how far they go from one to the other one, and there are some very interesting things to know about that. You see, for example, sometimes when you watch soccer on the TV, and you can see, or when you watch soccer, you can say, oh, the rear ones are too rear, and the forward ones are too forward, and there is no link in between, you see? So they wanted to know when this did happen, how this did happen. So that was the main focus of and the main interest of the coaches, but the ball is very interesting, and scientifically the ball is an additional problem. So what I talk about, the simulator like that, was an example, but we can use, for example, if there is a camera, you have someone with a camera, and we want to know who is the speaker and who is the audience and so on. We know it because there is mainly blue here and not on the other part and so on. If you have a square and you want to know if there are some problems on the square in the town, you can catch the area that is of the main color and so on. So there are many other applications. Other questions? If there is, yes, I would say something else. If there is something you didn't understand, do not hesitate to ask me, And if you are ashamed to ask in front of everyone, you can ask me by email, also directly, and you can find my email address on the internet. It's jean.sequeira at orange.fr. But if you type Jean Sequeira on Google, you will find my webpage and so on, and there is my email address. So you do not hesitate, you can send me an email telling me I was at your charla, at your conference, at your presentation, and I didn't know about projective space, or let's say I don't know, and I can send you some documents and some explanations if you want, even if you are ashamed to ask questions in front of the other ones.
Pueden preguntar en español también si desean.
Was it okay with the English? No podía hacerlo en español porque no hablo español muy bien. Una otra vez es posible. Y tendré que aprender y que la misma tecnología que utiliza.
The same technology used for simulating or repeating a last play in a tennis game.
Oh, I don't think so. I don't think so because I don't know here, but in France, let me tell you one thing. It's very impressive to see how slow is the transfer of technology transfer. We start on this project 15 years ago. We found some relevant results within this one. We have improved that, but maybe 7 years ago. And we still work on it. And on the TV in France, there is a TV channel that is Canal Plus. They still use the mouse to click on the players. They do not use at all of that, even if it has been published, and there is no patent, nothing on that, so they could use that, but they use product in which there are a lot of persons who do that by hand. So I don't think it is used for tennis, but it should be. If it is the case, it's not us. But we would like to do that. Maybe for tennis in Peru.
Maybe we need some help for soccer.
Yes, I can play also, but I'm a bit old, but I still play. Yes?
How does the input look like in terms of landmarks? Because if I want to apply it to a different sport or anything else...
Very good question too. Very good question. So, in this case, in the case I showed, there were very relevant landmarks because we are close to the goalkeeper. So there are a set of landmarks like corners and so on. So that's true on the both sides, but it's not true anymore in the middle area. So in the middle area, it's much more difficult. But we solved it. But I cannot give a conference on that, even if I have something ready for that. So there are landmarks like that, but there are other pieces of information. For example, in the middle of the field, there is a circle. And this circle is transformed by projective transformation into an ellipse. Okay? And we have also designed a very robust algorithm to find in real time ellipses in an image. So, by using this algorithm, when we detect not only the lines and the corners and so on, but also all the rounds. If we don't see the goalkeeper area, there is a part of circle that is transformed into a part of ellipse. If we are in the middle, there is a big circle that is transformed into an ellipse. And by using, and we have all the landmarks in some way, we have the transformation completely by using the way the circle has been transformed into an ellipse. And by having also the middle line. So so I focused mainly on the color. And I just talked about the lines and the landmarks, but I could discuss about many other things on that. We have also interesting stuff on detecting ellipses and so on. So thank you for these very good questions. Very interesting.
¿Alguna pregunta más?
No más preguntas. Así te dice.
They are shy.
Ok.
Yo quiero saber si
Ahí ve.
movimiento. Ya sabes que estos en partidos.
Thank you very much.
Muchas gracias, un aplauso.